Thank you very much, Greg. It's a tremendous pleasure and honor to be here. I want to thank all the folks that put on this fantastic event, Rob, Amber, Greg, Ron for inviting me. This is totally informal, so please, we can interact as much as you like. Interrupt me with any questions. Reeves County is particularly special and near and dear to me for a number of reasons. I had the honor of monitoring the water quality of the San Solomon Springs in Balmorhea for 3 years in collaboration with the Apache Corporation. That was very interesting work. Normally, I am kind of the king of drinking all of the world's worst gas station coffee and staying in the worst hotels. And anytime you get to jump into like the ninth wonder of the world, the San Solomon Springs, it's a real treat. Today, basically Dr. Naco and Dr. Green covered everything. So as a Canadian, I can just talk about hockey for 30 minutes here if we want to do that. As I said, I'm from Canada. I came down here to play college golf, and like all failed college athletes, I pursued a Ph.D. in biochemistry, and I'm actually a cancer biologist, biochemist by training. And I was working on a treatment for chronic myeloid leukemia in Dallas at UT Southwestern, where this was 2011, where I would see on the news, fracking, energy independence, water's lighting on fire, people are getting sick, animals are dying, great economic prosperity. And there were all these sensational claims, and there wasn't really any peer-reviewed data to support any of these. Dr. Nako's work here, he leads the world-class group. They published a lot of papers on this, but in 2011, we really didn't have a breadth of information. So in an unconventional fashion, I went out on my weekends, on my copious free time, and collected samples of people's water wells in the Barnett Shale, the Dallas-Fort Worth area, and tested them for the chemicals used in hydraulic fracturing. We published that paper in 2013, and I've been in this field ostensibly ever since. I've traveled all over the world. I've been involved in some of the most high-profile litigation, and it wasn't until about 2016 that me and my research partner, Dr. Kevin Shug at UT Arlington, decided it was probably better off that we work with the industry and work with various folks on solutions as opposed to just going out there and identifying problems. There are plenty of problems in the industry, as we've seen. Some of this is unbelievably appalling, but it behooves all of us to work together on some solutions, and that's kind of what I'm going to be talking to you about today. I'm going to be talking to you about the opportunities for some of these waters after it is treated. This topic has been covered extensively and extremely well by the previous presenters. I'm going to talk about the amount of water we're dealing with here, the types of treatment that are required to reuse it internally in the industry known as recycling, why recycling isn't enough, and then I'm going to talk about beneficial reuse, which basically means how do we repurpose this water to take it out of the oil and gas industry. And then also, are there opportunities for valorization to bring value to this water or extract value out of this water to kind of offset some of these treatment costs? So we've talked a lot about 15 to 20 million barrels of water a day. This is a relatively outdated paper, and this is how quickly science moves. This is 2023. Where they're showing that maybe peak water production may hit 20 million barrels by 2028, but then water production rates are going to drop down pretty considerably. So maybe we're out of these neck of the woods where we don't have this issue. The issue that this particular study doesn't account for is that all of the premier rock in this region, and it's like a sandwich. There's multiple layers in this sandwich to pull out oil, natural gas, which also comes with water. And the really, really good part of that sandwich has been mostly exploited to where we're now going to the second part of the sandwich, which unfortunately has more water. So you have a larger water cut and less oil, more water. So quite frankly, if we're going to continue to operate in this region, this number could level up, even maybe go higher. And so we are dealing with an incredible amount of water. And right now, the industry, if we're producing 15 to 20 million barrels a day, the industry, and actually I should go back here. What we're talking about here at 20 million barrels a day, that's over 1,200 Olympic swimming pools of water a day. That is 2,500 acre feet a day. That is a tremendous amount of water. This water is particularly salty, has been alluded to, anywhere from 16 to 20% salt. It's got a whole bunch of other stuff in it as well, which I'm going to touch on here. Approximately half of it is being used internally. That wasn't always the case. I would go to these energy conferences maybe 5 years ago, and energy companies were still using a lot of fresh water, and they had to adjust their downhole chemistry to account for the higher levels of salt and calcium and magnesium, which they have evolved considerably, and now the industry is using as much of this treated produced water as they can. Raw produced water is, sorry. There I go being Canadian, just apologizing out of nowhere. Okay, raw produced water is arguably the most complex milieu of biogeochemical constituents on the planet. You have hydrocarbons, you have chemical additives, you have metals, minerals, naturally occurring radioactive material, you have a wide breadth of microbial contaminants in these waters, mainly extremophiles, meaning bacteria that love extreme environments, different salts, and I'm going to use a beer analogy to kind of describe how this water is treated along the way. So if we go here as raw water, it certainly doesn't smell, certainly doesn't taste like Guinness Stout. And then after ozonation or any form of oxidation in this industry, if you're not using ozone, you're generally using hydrogen peroxide. Some people are using dissolved air flotation coupled with a flocculant to remove the hydrocarbon material and precipitate out key metals. Well, now you're left with probably an amber ale, and then after we pass that through particulate filtration, in many cases they're using what's called fractal glass here in the industry. That is just fancy terminology for crushed up beer bottles. Now you've taken all that flocculated material that resulted from the oxidation process, you've filtered that out, and you're left with something that looks like, maybe a Hefeweizen. Now the industry generally in this part of the world doesn't go in with primary, secondary carbon, but that would be a polishing step, and I'll talk about that a little bit later on. But now we have something after primary carbon, and this could be activated carbon. Now we have something that looks almost like fresh water, although it has 16 to 20% salt, a lot of dissolved material. And then if we go and treat this even further, now we got something that looks like Miller Lite here over on the far right. Again, the industry is using about half of the water that they're producing. Most of the work that I've done recently in the last couple of years has been in Eddy and Lee County, southeast New Mexico, the Delaware Basin. They are producing more oil per day than the entire country of Venezuela. They're producing over 1 million barrels a day, and they're producing about 5 to 5.5 million barrels of water. Now, the issue, which was covered so brilliantly by the two previous presenters, and actually I'm paying a small homage to Dr. Nakoh here in illustrating one of his papers, is if we are currently using half of the water, the other half of the water has to go away. It is essentially a nuisance. We do not have the regulatory framework currently in place in New Mexico or Texas to allow us to treat this water and take it outside of the oil field. Irrespective of how clean, safe, and non-toxic, there are no rules that allow us to take it out of the oil field. So the only application that we can use here for disposing of this water is subsurface injection. Well, what we have noticed over basically the last 10 years and more, it's been further accentuated in the last couple of years here, is an increase in frequency and magnitude of earthquakes. Dr. Nakoh mentioned magnitude 5 earthquakes. I think we had a 5.5, maybe even a 6 that was felt in El Paso. It was a Friday night. It was 10 o'clock, which is way past my bedtime, but I did feel it. My wife and kids thought if something weird had hit the side of the house or something like that. It was very strange. And fortunately we have the TexNet network who monitors this with the seismology, and basically the next morning we found out that, yeah, it was happening not too far from where we are here today. Also, as Dr. Naco mentioned, you have this surface deformity. So I kind of liken this to when I lived in Dallas, and you build your house on this clay, and they tell you have to water your foundation or else the foundation is going to shift. And so it's like, well, who really cares about 1 inch, 2 inches here and there? Well, that can have you look at a foundation shifting and cracking, that can have profound impact on your property value. And so I think cumulatively, as we have more of these seismic events, as we have more of this topological deformations, we are going to have infrastructure issues, property damage. And so the question is, how much longer do we have here in terms of figuring out a better way of managing these volumes? It's quite clear that subsurface disposal is required currently, but it's not the sustainable solution moving forward. And so the question is, are we 2 minutes to midnight? Are we an hour to midnight? What are we, right? Not to look at it through a doomsday perspective, but I am of the opinion that we might be 15 or 20 seconds to midnight here. We have to do something right away. Now, fortunately, we have a lot of really great science that has come out in the last couple of years on the beneficial reuse front. So I'm a UTEP guy, University of Texas at El Paso. So it's incredibly unlike me to want to say anything positive about anyone at New Mexico State University about anything. However, I have to say on the beneficial reuse front, these people have been absolutely world-class. Dr. Yan Zhang, Dr. Ph.D. have basically taken a very translational approach to figuring out, okay, how clean is clean enough so that we can take this out of the oil field and use it for various applications, and what technologies do we have to utilize to get there? So, as I mentioned to you before, we've got our raw water, our Guinness stout, if you will, okay? We're gonna do this pre-treatment, which is gonna be our oxidation, is gonna be our fractal glass filtration. So now we have what's called a clean brine that can either go into direct recycling and in the industry, or is now our feedstock for desalination. There's basically 4 different modalities to desalinate this water. We heard an excellent presentation about membrane-based technologies. That's certainly one of them. You have thermal-based processes. We now have solvent-based desalination. There's a very interesting company called Aquafortis who are operating a pilot facility in Colorado City. I recommend anyone check that out. And then you have solar desalination, something called humidification, dehumidification, which is something that's very energy efficient, but requires a tremendous amount of footprint in order to produce considerable yield. And what the New Mexico Produced Water Research Consortium has unearthed for us is that, okay, very, very complex mixture of hydrocarbons, chemicals, metals, minerals, naturally occurring radioactive material, bacteria, you name it, is in this stuff raw. Okay, then we treat it, we remove those major contaminants, now we have a clean brine, we still have 16 to 18% salt, high levels of radioactive material, calcium, strontium, still a lot of inorganic material. We desalinate it, so now we're down below the drinking water standard of 500 milligrams per liter. We still have residual contaminants in there. We still have residual hydrocarbons. We still have high levels of ammonia. Raw produced water in the Permian Basin has approximately 600 milligrams per liter ammonia, which has tremendous application in an agricultural context, something I'll talk about here in a second. But you still have residual amounts of metals that are leading to a toxicological signal. So that's a problem. And so what they found is what they call, or what the industry is now calling, post-treatment. So after desalination, you then pass this through granulated activated carbon. And ma'am, no need to take pictures. If anyone wants a version of these, it's okay. If anyone wants a copy of these slides, please shoot me an email. I'll happy to share them with you. This is important science that everyone needs to have access to. So they found that if you pass the water through granulated activated carbon, that's going to capture your residual hydrocarbons. And then if you pass the water through zeolite, which is just clay, effectively, it's going to capture your ammonia. And now they've done an enormous amount of toxicological screening down to a molecular level, which I'll go through here in a second, to show that this is cleaner and less toxic and safer than drinking water. And they can do this for less than $1 a barrel, which is something we'll talk about here in a second as well. But what about the unknowns, right? If this is the most complex milieu of chemicals out there, what about things that we don't have analytical metrics for? Right, we have a set number of things that we can test for in the lab, but we don't know about all the proprietary chemicals that are used in hydraulic fracturing, so hence we may not know about all the proprietary byproducts that could be in these waste streams, and how do we know that we're capturing all those in the treatment process? So there is a lot of folks doing a deep dive, my colleague Dr. Shug included, who are using some of the most advanced instrumentation going down to parts per quadrillion levels to understand what is left in here. What I want to convey here is that I think that that sort of mentality, what is in your treated produced water, we should think about what is in our drinking water in the same context, right? What my research has shown, and this is unpublished, is basically as we go from raw water, on the left here I have LCMS analysis. It's called liquid chromatography mass spectrometry. This is looking at semi-volatile compounds, things like chlorinated solvents. On the right here, we have gas chromatography mass spectrometry, which is a fancy way of looking for volatile carbons, things like benzene, toluene, ethylbenzene, various hydrocarbon contaminants. And if we go look at the color-coded stuff here, I've got raw water, I've got pre-treated water, so this is oxidation and filtration, then we have desalinated water, and then I have control water. I was naive in thinking that, well, I'm going to collect water from my tap here in El Paso, I'm going to collect water from the University of Texas at Arlington, I'm going to collect water from Houston, and this water is going to be great. It's going to pass all the toxicological assays, it's going to be fantastic control. And what we find here is when we do this screening for untargeted or non-targeted analyses to see what are those unknowns, there's absolutely no statistical difference between the number of these species in the water after produced water has been desalinated to our controls. If we go a step further and we look at acute, meaning short-term, and chronic, meaning long-term, toxicity assays, basically, the higher the value here, that means that your tox assay basically had no impact on the organism. That means it's non-toxic. If you had a very low tox screening, that means that was a highly toxic thing that had a profound impact on that organism. Not surprisingly, raw and pre-treated water is highly toxic. That's not going to surprise anyone. At this point in time, it still has 16 to 20% salt, 4 or 5 times the level of seawater. And after desalination, there are still samples where it is highly toxic, but there's also samples where it isn't toxic. It depends on the level of polishing. But if you remember, as I mentioned before, the New Mexico folks have found that desalination is not enough. It has to go to post-treatment to remove that ammonia and remove those residual hydrocarbons. But what was interesting is to find that you take drinking water samples and they don't do very well on the tox assay as well. So while we absolutely need to be doing a deep screening dive on treated produced water for all of these unknowns, we also need to have the same level of scrutiny on our drinking water. That's just my 2 cents. I'm Canadian, so it's worth even less. So but I think we need to scrutinize it very, very heavily. Now, regarding these unknowns, the toxicological, which is basically we're looking at things in a biological context. It started with how do these bacteria do in this water? Then it was how do these algae do in this water? Then it was flathead minnows, and you're looking at larger aquatic organisms. It has then gone to cell lines. So we're taking regular cells from humans, we're taking cancerous cells from humans, and now we're even looking at it at the molecular level, looking at individual proteins. So I got 6 minutes here, I'm gonna keep rocking and rolling. So in this is a recent study, they're looking at cytochrome P450. Cytochrome P450 is a liver enzyme that basically helps you metabolize external and exogenous compounds. Regardless of what it is, your body is going to be triggered by expressing or producing more of this enzyme in the event that it experiences a toxicant. So basically what this shows us here is that, okay, here is our control, the amount of expression. This is basically looking at a low temperature distillation system versus mechanical vapor recompression. So basically 2 thermal-based technologies desalinating the water. And we're looking at controls we're looking at raw water, we're looking at distillate water after desalination, and then we're looking at after post-treatment, the activated carbon and zeolite. And basically what these people found is that, okay, here's your basal level of P450 expression, which obviously goes up in the exposure to the raw water, okay? And even there's a profound impact to the distillate, meaning there's other stuff left in that water after distillation or desalination that your body is responding to. However, it goes right back down to at the same level or below the controls after the polishing. So to me, if we are showing that if we do this polishing, it's not going to affect organisms, it's not going to affect tissues, and now it's not going to affect your protein response at the molecular level, that tells me that this water is as safe as it can be. And again, if we were to look at drinking water sources here, they would be far worse, based on my experience of screening those as well. Okay, so now that we know more or less, and we've learned a lot in the last couple of years of how clean is clean enough and what technologies are required to get there, we're having a better understanding of the economics of these things. I can say, I can imagine that Ron is thinking of a question here about throughput and economics. 4 or 5 years ago, there were companies like Eureka Resources desalinating water, and they were doing 50 to 100,000 barrels a day for $4 a barrel and dumping this in the Susquehanna River. And they had a permit to do that because the solution to pollution is dilution. We're not talking about that here. We're talking about, can we take this? We don't have the Susquehanna River to dump into. We have the Pecos River. We're not allowed to put it into the Pecos River, even though this water would be cleaner than the Pecos River. But we need other outlets to do this. And so one of the major outlets that I see here is agriculture. I mean, this is a no-brainer. So if we're producing 15 million barrels a day, and half of that's being used by industry, now we have 7.5 million barrels that we can use, and generally a very good desalination process will have a 50% throughput. You're going to get 50% fresh water, 50% reject, which is going to be about 30% salt. So now we got about 3 million barrels of water a day that we could be producing in this region that could go to the agricultural community. And as I showed here, one of the things that we can toggle is basically, we can leave the ammonia in there. After desalination, we can run this through carbon, and we can remove the hydrocarbons, any residual, and we're talking parts per billion levels that are being removed. But if we don't pass it through the zeolite, now we still have residual ammonia, which has agricultural value. And so one particular crop that I get a lot of laughing about this. I've been in the medicinal cannabis space researching this very heavily for the last 10 years. I got into this as basically the new frontier of medicine. And a lot of people will say, well, it's just the devil's lettuce, it's marijuana, it's the jazz cabbage. All of those monikers are basically terms used by the paper industry to demonize hemp, because they knew if this hemp stuff caught on and people understood this is a way better textile than these trees we were cutting down, so we need to demonize that. And that's where a lot of these terms, God forbid we take something like the term jazz cabbage, God forbid we use something and put it in our body that allows us to enjoy jazz music and have a good time. Hemp is an interesting one because, one, it is incredible at phytoremediation, which basically you plant this and it will rip metals out of the soil. That is fantastic. Secondarily, it is a very powerful crop for textiles. We can make hempcrete, papers, can build houses with it. But most notably, it is an incredibly powerful therapeutic agent. This is a close-up view of these little glass balls are called trichomes, and they have various cannabinoids, which are the medicinal elements. They also have fragrance elements called terpenes, and they have antioxidants called flavonoids. And so I have seen epileptic children basically stop an epilepsy within 15 seconds of taking certain formulations. I've seen cancer patients prolong their life by 20 years as a result of taking this medicine that they've been taking since the 90s. I have seen skin conditions and neurological abnormalities been greatly improved by various constituents found in this plant. So here we are we could literally kill multiple birds with one stone. We could use this water in an agricultural context, and then we could also produce products and medicines. There's a couple people I'd like to mention here. So you got Charles and Marvin out there. So basically, as we go through this process, and you want to grow different crops, that's going to require different formulations of the water, and there's going to be different soil chemistries. And these gentlemen have a patented process that allows us to account for all of that while also providing protections if anything goes wrong during a batch of this. So that's a very, very important aspect of this entire paradigm. And then also Eric Sellinger. He's someone who you may have heard of, his Imperial Oasis project there. It's something that I want to get heavily involved with. He's trying to bring back a beautiful part. West Texas is a beautiful part of the world. Many people regard it as God's country, and he's trying to bring it back to prominence by bringing back agricultural activity and bringing back value. And water comes with value. And so if we can use this water, now that we know how it can be used effectively, we can use it safely and sustainably, and we can bring value to this region and turn it into an oasis like it once was. Now, one question that you may have is, okay, Zach, you've talked about how to treat it so for industrial use. We've talked about how to use it outside of the oil field. You're talking about desalinating it. How are you going to manage all of the salts, right? You're going to rip all that salt out of this solution. We are going to have the Swiss Alps or the Pyrenees of sodium chloride out here in the Permian. Well, I'm going to get to that in a second here, and I'm over time, and I apologize. I'm going to be a couple more minutes here, I promise. In Permian produced water, and this is basically looking at produced water composition from the Bakken Shale of the Dakotas in the Permian Basin here, obviously. Sodium is the predominant constituent. It doesn't have a lot of value, but I'm going to get into how it can be repurposed into something else. For the longest time, lithium, it's still very much in vogue. Lithium commodity prices have come down a lot. Unfortunately, Permian produced water has a very low level of lithium, about 20 milligrams per liter. And irrespective of how much or how effective people have been at extracting lithium hydroxide or lithium carbonate out of the water, there haven't really been a robust marketplace for offtake. So that's really hindered that whole initiative. You also have strontium, calcium, magnesium, and there's a lot of stuff in this water that we could find a home for that could create value. Here's the sodium chloride Pyrenees of the Permian, right? Now, how this would work, again, you go through your process, you got the raw water, you're skimming it for oil, so that skim oil has value. Then it's going through oxidation and filtration. You're able to rip out certain hydrocarbons, things like pyridine, which have value. You do the desalination, now you've produced this salty slurry that you can then mine it for various constituents here. And then you've got your post-treatment that then produces this fresh water. And my whole goal with some of this, working with folks like Eric, is if it costs $1 a barrel to treat this water, I would like to find $1 a barrel in that water so that we can then give it to the farmers for free, so that they can use this water. These people take enormous risk and put a lot of stress on their plate to produce our food. So I think the least that we could do is give them the water that they need to do their jobs. And so I started working with a very interesting, clever gentleman out of California, Joe Zubak, who's done a lot of calculations. He's very interested in these multivalent salts, so things like calcium chloride, strontium chloride, magnesium chloride, as a way to produce these chemicals or these compounds that could really offset the treatment costs. And going back to this one slide here, right here, all of this sodium chloride, we have a process called chloralkali, which can transform sodium chloride into hydrochloric acid, which is something used ubiquitously in hydraulic fracturing, and sodium hydroxide caustic, which is used in the industry as well in water treatment. And there are entities like Blue Brine who have haven't even built their facility. They're supposed to couple on with a desalination facility in my hometown, El Paso, where they're going to take the RO reject, basically a lull, the sodium chloride, and they already have offtake agreements for all the hydrochloric acid and sodium hydroxide that they're going to make for the next 10 years. And that's how they were able to finance the building of their treatment facility. So they're dealing with RO reject. We're dealing with something that's going to have a much higher salinity. So there's the potential for even more commodity extraction here. So to me, it seems like a greater opportunity. But again, none of this is going to happen until we have the rules of the game. No one is going to outlay capital and do all of these interesting things until we know that we can put the water on the ground, or we can put it in a stream, and we can do so safely and reliably. And my hope is that the science is going to speak loudly enough at this point in time that people start to feel comfortable with this. Because if we don't figure out, I'm not trying to sound like an alarmist here at all, if we don't figure out what to do with this water and take it outside of the oil field, we are going to have serious, serious problems. We cannot keep putting it into the ground. And what's that?
We already have serious problems.
Absolutely, clearly. I saw the previous presentation here, and it was both incredibly insightful and alarming. I had no idea that this oil and gas fraud was so prevalent. I guess I'm, incredibly naive. You could probably call me, 480 months old. Just I'm a baby in thinking that this kind of thing doesn't happen. But that was shocking. So we have to do something, and I think we're running out of time in order to do something profound. So with that, I'll take any questions. Thank you. Yes, sir.
Yes, I'm with IDE Technologies, and we have technology to treat and produce water thermally.
Okay.
And a question I've got, though, on the agricultural component side. You have a plan to treat this water with a thermal process. We end up basically with distilled water.
Yeah.
Question being, in agriculture, you don't irrigate cotton in February. That you need a place to go with that water every day of the year because you're running a plant. What is your thoughts on recharging fresh water aquifers, whether it's the Ogallala or others? What are the dangers you see in that? What is the regulatory pushback been? Because once you start a plant running to treat the water, you gotta have somewhere to go with it every day.
So you have three applications, right? You have surface discharge, you have aquifer recharge, and then you have you basically have agricultural utilization, right? And so if you're not putting it in the Pecos River or the Red Bluff Reservoir, which straddles the New Mexico and Texas line there, do you go ahead and build some of these large earthen pits that we see in the industry? Well, those are about $1 million barrel pit is $1 million, right? So that seems like a large capital cost to do that. So yeah, aquifer recharge does make sense. One concern is that with the thermal process, the water is too clean. In some cases, you have to remineralize it. So then how does that play a role in the groundwater chemistry there? So if I was to triage things, I think we're probably going to see surface discharge into streams and rivers first. Then we're going to see agricultural use, and then aquifer recharge probably tertiary to that. Thank you. Any other questions? Yes, ma'am. And then you there.
You mentioned that you use seal light
I'm sorry, say that again?
You mentioned that you use in the process seal light in the activated carbon.
Yes.
What do you do with that? Once it's depleted, once it's
That, so that's a great question. As of right now, we are using those in kind of pilot scale applications. So it really hasn't gotten to the big boy game yet, right? How much zeolite and activated carbon are you going to go through when you're doing 250,000 barrels at 10 different facilities, right? I think the zeolite, it turns into kitty litter effectively. So theoretically, could that turn into an agricultural amendment? If you're just sequestering the ammonia. Now the activated carbon is going to have the hydrocarbon contaminants, BTEX, various linear and polycyclic hydrocarbons. That's not going to be a soil amendment. We've all heard about that deal going on in Johnson County, Texas, where the city of Fort Worth is selling their bio sludge. and it's going to farms and it's loaded with PFAS and those people's farms, that can't happen here. So it's going to definitely have to be something we have to address, but nobody has looked at that. It's an excellent question because we're not operating at a commercial scale yet. I think you had a question, and then yes, please, sir.
Yeah, speaking of PFAS, so you did acute toxicity studies which would show a lowest observable adverse effect level in amino rate, like immediately. But what about like long-term chronic health impacts? Would those types of studies like show something that would build up over time and cause cancer or something like that? And like, what about, PFAS is kind of like the big thing that people are concerned about now. Would the toxicity studies you did kind of show an impact from that?
Yeah, that's an excellent question. So the work at New Mexico State, they've done some of these more advanced organisms where they basically looked at multi-generational type thing and looked at fish as opposed to bacteria. They're going to be a better indicator. One thing that I'm very interested in is doing a multi-year or multi-harvest crop study. So where we water a crop, we harvest it, we look at, let's say, tomatoes. And then we use that same soil again for another batch of tomatoes, and we see if is there an accumulation of anything in that soil. Also, in those tomatoes, we feed those to mice. What happens to those mice that eat those tomatoes, right? We need to understand the whole entire food chain. So that's research that I'm looking to work on with Eric, granted we get it funded. But yeah, we need to be looking at longer term implications for sure. I think some of the lower hanging fruit here, no pun intended, is if this stuff is as clean as we think it is, it could just be discharged into the desert so that we don't have to put it down whole and cause earthquakes.
And speaking of that, so Railroad Commission just finalized some new rules on land farming, land treating, land application of treated produced water. And then we have the National Pollution Elimination Discharge Permits, right? TCEQ.
Yep.
What rules do you think are still needed? Is it specifically for the application on crops, or is there something else that you're talking about?
So it's both. It's both, actually. So it sounds like the TCEQ, which basically just took over the discharge, because normally anything oil and gas would fall under the Railroad Commission's jurisdiction. I don't think handed it over is the correct terminology. It transferred, yeah. So now it's TCEQ's ball, right? And they have 5 permits, I believe, in the queue, so to speak. And so they have entities like NGL and Select that are looking to discharge up to 100,000 barrels a day in the Red Bluff Reservoir that straddles that state line. My understanding is that the regulators are looking at agricultural use as faraway cattle. Let's figure out how the surface discharge goes, and then we'll figure out if we can put this on crops. But we have so much water that we need to be exploring all outlets simultaneously. My concern is this wait and see approach. Like the science here is evolving incredibly rapidly, which is fantastic. And we can feel confident that, again, this water is every bit as clean, if not cleaner and less toxic than drinking water. So let's go ahead and start exploring its use in a wider application. And there was a question back there? Thank you, by the way.
For the purified water, have you looked into the process of, because you can have pure water and you can have pure salt and other minerals, right? You can separate them out. You can run that back through electrolysis. You can make ultra pure sulfuric acid.
Yes.
Sulfuric acid and ultra pure water is 2 of the biggest components that the electronic chip makers are searching for right now inside the United States.
So I wasn't sure about sulfuric acid, but I have looked at hydrochloric acid and sodium hydroxide caustic by chloralkali. You can make chlorine, yes. Yep. So I think what would be driving the valorization bus is people need to have offtake agreements lined up. Like this is the mistake that the lithium industry made is, okay, I'm gonna go out, I'm gonna get the best process, and I'm gonna make the most pure lithium carbonate out of this brine. Most of it's happening in Oklahoma or in the Marcellus where they have more favorable lithium concentrations, and then no one's buying it. The only commodity that anyone is buying out of produced water right now is iodine. IAFINA has a really cool process where they come in and they say, you don't pay anything up front, you don't pay anything to operate this, we're going to pay you a per barrel rate, and we rip the iodine out of here and we sell it into the medical application space, and they're doing really, really well with that. And so what I'm hoping to cultivate with a team of folks is, let's do that for ammonia, let's do that for strontium, let's do that for 5 or 6 constituents, so I can find $1 a barrel that then I can allow the farmers to get the water for free. Yeah, I mean, my understanding is a barrel of hydrochloric acid could go for like $1,000, right? $1,000. So I don't know how many barrels of produced water we need to produce a barrel of hydrochloric acid, but that could be a great way to offset costs for sure. Yeah.
Are you all looking for test sites?
Always looking for test sites, always looking for produced water, yes.